Hello, everyone. My name is Sahal Husseini, and I'm going to talk about word embeddings today. So, if you're working with natural language processing or large language model, uh, you know that these models don't cannot deal with text or categories. So, you need to find a way to convert them to number. So one of the tools that actually we can use that is word2vec, and I'm going to talk about a skipgram in this video. So and how we can actually convert text to vector continuous number. So and then we will be able to use that in natural language processing or large language model. So let's see how this works. So imagine we have this sentence: the white road shimmered in the hot sun. So we have two concepts in here. Uh, one is target word, and another one is context word. You see that in here. So target word is any word in your text. So the white road shimmered in the hot sun. So any of them is your target. And also you have a window size. So these are all the steps you actually we need to use them in word2vec skipgrams in order to calculate the word embeddings for any word that you have that in your sentence. So basically you convert them to a vector. So could be each word can have a vector of 128, size of 128 or 300 that could be used. So, so in this, in the first sentence, our target word is white, and there's a window with a size of 2. Could go 2 to the left, 2 to the right. And a scriptogram, that's a combination of these words. So white and 2 could be together. And there's only one word to the left. We have 2 words to the right of this white target. So we have white road and white shimmer, which is in our window size of 2. So you can change that window size as many as possible based on the length of sentence that you have. This is just another example. Target word is a shimmer, and the context window size is of 2. So you have 2 to the left and 2 to the right. So these two make one combination, and shimmered with white another combination. You'll see that in here, and shimmered with N and shimmered with N. So basically, I will tell you that these can come together in a sentence or a corpus and so on. So that's the whole idea. But how to figure it out, like this word can come before this target there, or road can come after that, or there is like it's not that my name can come after this. So there's a low probability my name coming after this white than the road. So how do we figure it out? So the whole idea is find the maximum probability for these words that it come after or before our target word. So how do we figure it out? And to calculate the maximum probability for these words within can be in the window size around our target. So in order to do that, in this case, we create an objective function, and I'll try to optimize that objective function. So in that case, we can calculate the word embeddings for every word. All right, so we have, in here, we have the equation in here. So you can see that this T is actually, this is all your words that you have in this deck. So so in this case, how many words that we have? We have 1 word, 2, 3, 4, 5, 6, 7, 8. So that T is 8 for this sentence. So you can have a corpus, you can have a novel, and so on. So that's how that would be the total number of words that you have. So, and you can see that it applies from 1 to t. It means that it consider this objective function. This is based on skip ram. It actually consider for every word. So for every word that we have, in here, what we're going to do that, we are calculating the probability of words in that window size. So whatever your window size is. So in this case, the C that you see that's the window size. So actually what we wanted to do, we wanted to figure it out. So this window size for sun is 3 in here. There's nothing after sun, but you have 3 words before that. And window size is 3. So in this case, we'll say that, okay, so WT, so T goes from 1 to 8 in this case, and it'll apply for every word. And this combination actually, the total sum of logarithm of probability. So how does this one work? So the J is the center or target in this case. We'll see that in here. So let's write that for this case. How does this one work? So T is, in this case, actually T is capital T. So the last word, and it's 8. So this equation, we see that in here, the last one, is logarithm of P. If I write that for each one of them, so it's look like it considers the whole window that you have. So in this case, we have only left side. So that would be logarithm of, if I have, the word is sun, what's the probability having in that window size, plus logarithm of same thing, the next word, probability of death. I have that in window size given sun, and the last one, probability of hot given word sun, and that would be sum up for every word. So that's for the last word or target word, and we calculate this the summation in here is sum over all words with the same idea. All right, so and this average, and you can see that this is actually average out. And the reason they're using that is we wanted to optimize this. We wanted to maximize this objective function. And you see that this probability small value. This is between 0 to 1. This is between 0 to 1, that probability. Each probability is between 0 to 1. And we take the logarithm. So this number is negative. So we wanted to have less negative number in order to get the maximum value for this objective function. What happens here, if you don't optimize that, so you don't have a metric if your document or size is different. So the number of words in like in one text is 8, or maybe the corpus has 10,000 words. So we actually average out to, so your score is not biased based on size. So, but where's this equation? So this equation, it's coming from another equation actually, which is written in sum. So the idea here is, but they actually wanted to optimize. The idea is this word, probably this road given shimmered, for instance. The idea is this one, this road given shimmer. What's the probability of having road in that window size given word shimmered is um, we assume that these words, like another word as white, given shimmer, we assume that these words are only depend on the target. They are not dependent on each other. So road doesn't depend on white or vice versa. So these are all independent. So what happens since they're independent, we can multiply all of them together. So originally this equation is a multiplication of all these probabilities. So originally this is like this. So we have given WT, and so we have the same thing in here. J is minus C, and this is C, and this is T L to 1, and I'm going to skip that 1 over T in here. So, but there's an issue here. The issue is these probability are all a small number, very small number. So imagine my corpus size is 10,000, for instance. And we have one probability, only one case, and this probability is 0.1. Okay, and all of them are the same number. In that, if you multiply them together, this objective function, for instance, would be 1.1 to the power of 10,000. So it's basically that would be very small number, underflow, and the computer cannot calculate that. So in order to do that, they actually take the logarithm of this equation, and that's what generate this one in this format. If you have this format, we actually would be very easy to take a derivative of this. The derivative would be linear. In that case, we can use gradient descent to we should use that next step in order to train the model based on the corpus we can actually, using deep learning, would be easily to calculate, to apply gradient descent and calculate word embedding. So this is originally coming from this equation. All right, so now, so this is a probability. What is this probability coming from? This probability, as you see that in here, for each one of them, it's coming from this equation. And this is softmax. This is softmax. For each case, we know that for the total, and this is WI is input, basically our I as input and O is output in here. And this is a softmax, and as you see that in here, these are V and V prime. These are actually word embeddings for each text that we have in here, and this is the inner vector. All right, so the idea is, I'm going to get back to this example in here. So imagine our input vector in here, input vector, or input vector in here, WI in here is sun. And we wanted to calculate the probability of this word, which is in the window size, which is hot. So this probability, so in order to calculate this probability, that would be multiplication of this inner vector between this output and word embedding of the input. So in this case, that's WO would be hot. So in order to do that, these are all vectors. Initially, they start we start with initial value will be trained based on the corpus, going through the deep learning, and at the end will converge to its final value. But these are actually this is the inner product between these two vectors, and this is the total inner product. How does that work? So first of all, this probability, if you have, so based on this input, so it could get any words, for instance, from this sentence. Okay, so it could be probability of, um, in this case, was hot, given sun. It could be the next one, the sun. It could be in, given what sun, uh, probability of shimmer, given sun, and so on. So at the end, so imagine it could be based on that's the whole words that we have. We have only 8 words. So there's sun. Um, the next word would be any of these 8 options. These options that you have. So the total probability must be 1 based on law of probability. So this total would be 1. So that's what you see that's a total option of probability that we have in here. And this is for only this 2 case. So and basically for every one of them, we calculate this inner product and divided by the total option of the probability. And based on this, we know that this is between 0 to 1. And this is what plugging in here. So you see that this is exponential. It actually helps us. We take the logarithm. Actually, would be very easy applying that, and basically we'll convert that to linear equation, and we can calculate the gradient descent. That would be very, very easy to calculate that. So this is the idea, and so this is the idea behind this equation. And again, this we need to optimize the equation. This equation going to deep learning model, and will be the word embeddings will be calculated. And they have on this one going through the whole equation, the whole code, and you actually can run that. All right. Another things I wanted to mention that. So I have a simple code in here. So in this case, this is actually GenSim is one of the libraries that actually you can use word2vec. They have pre-trained model. This is the pre-trained model based on Google News. Let's look into that. How actually word embedding, when I apply that based on this Google News, based on the size of data that they have, how actually word embeddings would be we will have for every word, and we can calculate that. So see that, okay. When we have a few terms in here. This is the pre-trained model. I actually load this pre-trained model, and it has lots of words that you can look into that, and we can go through its word embedding for every word that available in that context. So in this case, for instance, I'm looking the word cat, and it will give me the first 10 items of that vector. So you can see that this is the first dimension of that. And you can actually get the whole vector. So that's what basically you can use that in NLP, natural language processing, or you can use that in large language model. This is also another function, gives you most similar word, top 5 similar words to cat. One thing when we talk about similarity, this is talking about cosine similarity. So this is about cosine similarity. And so for any vector that you have cosine similarity, so we have if you have if I have two vector v1 and v2, the cosine similarity is basically inner product of these two divided by their value. So if I had two vectors, this v1 and v2, this is v1 and v2, that cosine similarity, that's the cosine value of this theta degree between them. And this value based on this cosine, so that would be between -1 and 1. When words are very similar, and they all use the same context also would be in the window size that we have that. The similarity would be very high. This degree would be very small. So this value would be very close. So this theta would be maybe very close to 0. And this value would be very close to 1. And if they are not similar or not in the same text, same sentence, same corpus, this theta between v1 and v2 is the vector. So I'm showing that in 2 dimension, but the idea is the same thing. It could go work in a higher dimension. In this case, the word embeddings that we have is just in the higher dimension. It could be 128 vector of 128 or 300. And this theta would be 90. So that cosine this cosine of this one would be almost 0. So they are basically not similar or unrelated. So, and here it actually showing me based on this Google News, all the context that they have that pre-internet Google News, it will show us the most top 5 similar word to cat. So in this case, it's going to print out the words similar to cat. We'll see that cats that we have, that dogs and kitten and bagels and so on. So if they are very similar, then we see that this is the similarity, and it goes very high, could go close to 1. We'll see that the highest one goes to close to 1. And in here, calculate the cosine similarity between cat and dog. We'll see that it's 0.76. And if I look into that cosine similarity between cat and sat, we'll see that this number is very small. And also I have checked the similarity, cosine similarity between female and male. So we see that this value is 84%. Again, this is the model is pre-trained based on Google News in here. So, and you can see that these are basically used that in the same context. So you see that in this case, you see that these words are very, very similar. Not cat and sat. So this is going through, it is close to 0, and this one is more, it's closer to 1. So we see that these words are more similar. So, and also in this case, you can get the whole vector, total vector in here if you wanted to, see that the whole vector. Let's run this one more time, and we can see that the whole vector is, and I can print the vector size. So we'll see that what's the size of this vector. Let's run this. It might take a little bit, and we'll see that what we get for this. So, and so there are a lot of pre-trained model for word embeddings. This is what to back using scriptgram, and this is a library that you can use that gensim. So you will need to install that library. Yeah, it has some dependency that you can use. Need to be installed, and this is what you can use that if you wanted to work with large language model in order to work with that. So the default in here is the vector size is 300, and that's for the word cat, and we can use that for any word that we have that in that corpus. All right, I think that's enough for this video. Thanks for watching, guys.